Have you ever stopped and wondered how an email you send from your laptop just magically finds its way across the globe in seconds? Well, it's not magic. It's actually a super sophisticated navigation system. And today, we're taking a look at one of the internet's most important traffic cops, OSPF, a protocol that acts like a GPS for your data. I mean, really think about it. The internet is this sprawling, kind of chaotic mesh of connections. When you send something, there isn't just one path. There are thousands, maybe even millions. So how in the world does it know to take the superhighway instead of getting stuck on some scenic, dead-end country road? That is the exact problem OSPF was built to solve. Okay, let's break this down with a simple analogy, because this makes it all click. The old way of routing data was like stopping your car at every single intersection to ask for directions. It's slow, it relies on hearsay, and you might even get sent in circles. The OSPF way? Totally different. It's like every car on the road suddenly gets a live, constantly updated GPS map of the entire city. No more asking, just smart, efficient driving. So what does it actually mean when we say we're giving our data a GPS? Let's unpack how this powerful analogy really works under the hood. So here's the official name, Open Shortest Path First, or OSPF. Now the key term you gotta remember here is link state. I know it sounds technical, but it really just means map. Instead of only knowing about its immediate neighbors, a link state protocol like OSPF works by building a complete topological map of the entire network. And this just perfectly highlights the problem with those older protocols, like one called RIP. They were distance vector protocols, which is just a fancy way of saying they relied on that asking your neighbor method, or, what we could call routing by rumor. A router running RIP only knows what its direct neighbor tells it, which, as you can imagine, can lead to some really slow updates and pretty bad decisions. Okay, so if every single router has a map, how do they build it in the first place? And maybe more importantly, how do they keep it updated in real time? Well, the whole process starts, piece by piece, with a simple hello. So it all starts with a friendly introduction. First, routers send out these little hello packets to discover each other. Once they connect, they form an adjacency, which is just a formal neighbor relationship. And then comes the really crucial step. They exchange their complete map collections, what we call link state databases. Once they have identical maps in hand, each router can independently figure out the best path to every single destination. This link state database, or LSDB, is the absolute heart of OSPF. I mean it. It's not just a list of directions. It is the master map. And the most important part is that every single router in the same area has an identical copy. This shared, consistent view of the network, that's the secret sauce to its reliability. Right, so you have the map. But how do you find the quickest route from point A to point B? Well, that's where some pretty clever math comes in. OSPF uses something called Dijkstra's algorithm. Now, you don't need to know the complex math behind it. Just think of it as the computational engine inside your GPS that instantly calculates the best route based on the map it's looking at. So we get it. OSPF gives every router a map and the math to read it. But why does this matter? What are the real-world benefits of doing it this way? Let's break down why this map-based system is just flat out better. First up, fast convergence. Now, convergence is just what we call it when all the routers agree on the network layout. If a connection goes down, think of it like a sudden road closure, every router with the map knows about it almost instantly. They all just run their GPS math again and find a new route. This is so much faster than waiting for the news to spread from neighbor to neighbor. OSPF is also incredibly efficient. Think of it like this. Instead of mailing you a brand new, complete city map every single hour, your GPS just sends a tiny little alert when a road closes or a new one opens. OSPF routers do the same thing. They only send out small updates when the network actually changes. It's quiet and it saves a ton of resources. This map-based approach is also extremely scalable. For huge networks, trying to maintain one single gigantic map for every router would just be overwhelming. So OSPF cleverly divides the network into what it calls areas. A router only needs a super detailed map of its own area, and just a summary of how to get to other areas. It's kind of like how you know your own city's streets perfectly, but you only need the main highways to get to another state. And finally, you get rock-solid reliability. Because every single router is working from the same, identical map, it's pretty much impossible for data to get stuck in a routing loop, where it gets passed back and forth between two routers that have conflicting directions. With OSPF, there are no conflicting directions. Everyone agrees on the best path, period. So how do all these routers talk to each other so efficiently? Well, they use special multicast addresses. You can think of 224.0.0.5 as a special radio frequency for all OSPF routers. It's like a group chat for every mapmaker. The second address, the one ending in .6, is used to talk to the designated router, or DR, who is basically the elected leader on that part of the network that helps keep all the conversations organized. It's all about smart, efficient communication. All right, we have covered a lot of ground here. Let's try and distill all of this down into a final cheat sheet with the most important takeaways you really need to remember about OSPF. Okay, let's lock in these key ideas. Just remember, link state equals the map method, while old protocols like RIP used gossip. In big networks, everything has to connect back to the mandatory backbone, which is area 0. The best path is figured out by cost, which really just means the fastest link, the one with the most bandwidth, wins. It's a classless protocol, so it's flexible and really efficient with IP addresses. And finally, it's an open standard, which means it isn't locked to a single company's hardware. You see, OSPF is just one piece of this incredible puzzle, a fundamental rule that brings order to the chaos of the internet. It shows us that just beneath the surface of our seamless digital experience, there are these elegant systems and maps guiding every single packet of data. So the next time you hit send, remember that invisible GPS at work. It makes you wonder what other hidden protocols are out there, making it all possible.